Magnetic fields are a constant presence in the physical world. They permeate galaxies, atoms, and even our own bodies, yet they remain entirely undetected by human senses. A common bar magnet appears solid and static. However, it is continuously projecting a hidden structure of force into the space surrounding it. To reveal these physical laws, we can use a dusting of iron filings as a visual medium. When sprinkled onto a glass pane over a magnet, these tiny metal shards serve as a physical bridge to the unseen. This top-down view shows the immediate result. The magnetic field snaps the chaotic dust into a symmetrical structure, turning a vacuum of knowledge into a visible map. The filings align along precise geometric paths, providing a direct physical translation of the magnetic force. This organized structure provides tangible proof that the area around a magnet is governed by a precise physical architecture.
At the two ends of the magnet, the iron filings cluster with the highest density. These concentrations indicate the points where the magnetic force is most intense. These two centers of influence are known as the North and South poles. Because the force is anchored by these two opposing points, this configuration is called a magnetic dipole. This structure is characterized by force flowing between two distinct polarities, much like the attraction and repulsion observed between positive and negative electric charges. The names North and South reflect how a magnet interacts with the world. A magnet allowed to rotate freely will always align itself with the Earth's axis. This antique compass demonstrates that exact behavior. By allowing a small magnetic needle to spin without friction, early navigators could track a consistent heading across a featureless ocean. Unlike electricity, where you can separate a positive charge from a negative one, magnetic poles are inseparable. Breaking this bar in half simply results in two smaller, complete dipoles. The orientation we see in a handheld magnet is a local response to a global phenomenon. Every compass on the surface is aligning with the Earth's own massive dipole, using these small-scale geometric rules to navigate the entire planet. In the early 19th century, physicists like André-Marie Ampère began to suspect that all magnetism stems from the same source, circulating electric currents. We can test this using a solenoid, a cylinder wrapped in a coil of wire that carries an electric current. If we scatter iron filings around this active coil, the shards settle into a pattern that is virtually identical to the one produced by a solid bar magnet. This proves that the field produced by flowing electricity and the field produced by a solid magnet follow the same mathematical principles. The matching patterns confirm that magnetism is a phenomenon that links the behavior of solid matter directly to the movement of electric charges. In this high-contrast view, we can clearly see the filings tracing curved paths that connect one pole to the other. Physicists call these visible traces magnetic field lines. They serve as a conceptual map used to visualize the strength and direction of the magnetic force at any point in space. These lines are continuous, closed loops. They emerge from the North Pole, arc through the surrounding space, and dive into the South Pole to continue through the magnet itself. Because the magnetic field has a unique direction at every point, these lines can never cross. If they intersected, it would imply the force is pulling in two different directions at once. While iron filings on a glass pane show a flat pattern, the actual field occupies three-dimensional space around the magnet in all directions simultaneously. The patterns we see on a table are two-dimensional cross-sections of a much larger, invisible architecture that surrounds every magnet in the world.